Welcome to this session. In the previous session, we have seen the basic idea of a recurrence relation. In a nutshell, a recurrence relation is an expression that is used to define a series, the nth term of a series. A recurrence relation is an expression which is used to specify the nth term of a series by using the previous terms of the series. Say for example, once again if I take the example of a Fibonacci series, then the nth term, if I denote the Fibonacci series by let us say f, then the nth term of the Fibonacci series is defined by f of n minus 1 plus f of n minus 2. So we all know that the Fibonacci series, each term is the sum of the previous two terms. Now a recurrence relation needs a little bit more than just this expression. It also needs the initial values. In case of Fibonacci series, we know that f1 is equal to 1 and f2 is equal to 1 if I want to start the expression by 1. If I want to express the first term as f0, then it would have been f0 is equal to 1 and f1 is equal to 1. So in the previous session, we have seen what are recurrence relations. We talked about the order of the recurrence relation. Order of the recurrence relation essentially means on how many previous terms does the current term depend on while specifying the recurrence relation. In other terms, the order of the recurrence relation is the difference between the largest and the smallest subscript. So the difference between the largest and the smallest subscript is called the order of the recurrence relation. Say for example, this recurrence relation that I have shown over here is a recurrence relation of order 2. We also specified what do we mean by the degree of a recurrence relation. The degree of the recurrence relation is the largest power of any recurrence term. If you see over here, the three recurrence terms, they all have the power 1. So we say that this is a recurrence relation of degree 1, and recurrence relations of degree 1 are called linear recurrence relations. Right? In this lecture, we are going to talk about the solving the recurrence relations. Towards the end of the previous session, we said that there are three methods of solving a recurrence relation. The first one was the iteration method, second one was the characteristic root method, and third was the generating function method. In this session, we will be talking about the iteration method. Let's start. So once again, if the degree of a recurrence relation is 1, then the relation is said to be a linear recurrence relation. This is the general form of a linear recurrence relation. C0 an plus C1 an minus 1 plus C2 an minus 2 up to Ck an k is equal to Fn, where C0, C1, C2, these are called the coefficients, and an minus 1, an minus 2, an minus k, these are the recurrence terms. Right? If the coefficients C0, C1, C2 and all are constants, then it is called a recurrence relation with constant coefficients. And if they are not constant, then it is called a recurrence relation with non-constant coefficients. As you can see, this once again, this recurrence relation is of degree 1. See, all the recurrence terms are of power 1. So this is called a linear recurrence relation. Now this Fn is a function that satisfies this recurrence equation. If this function Fn is equal to 0, that means if this expression C0 an plus C1 an minus 1 plus C2 an minus 2 up to Ck n minus k is equal to 0, then it is called a homogeneous recurrence relation. And if Fn is not equal to 0, then it is called a non-homogeneous recurrence relation. Now, when we say we want to solve the recurrence relation, what do we actually mean? We want to find an explicit formula for the nth term of the series which is not using the previous terms. Remember, the recurrence relation is an expression for the nth term of the series using the previous terms. And if I say the solution of a recurrence relation, it is an explicit formula. Here, the nth term is specified without using the previous terms. As an example, I can say if this is the recurrence relation that has been given, an is equal to n minus 1, and I have given you the initial condition a0 is equal to 5. The solution to this particular recurrence relation is an is equal to 5 factorial. An is equal to 5 factorial. So again, the most important point is the solution is not using any of the previous terms. We will see, we will solve this particular recurrence relation in the subsequent slides. Now there are three methods of solving in recurrence relation as I mentioned earlier. The first method is called the iterative method or the iteration method. In the iteration method, the recurrence relation for an is used repeatedly to solve for a general expression for an in terms of n. Although I know this definition seems a little bit cryptic, but it will be clearer once we solve the examples. One more thing, before we actually start solving the recurrence relations, there are two things that are important. Again, we all know what are arithmetic progressions and geometric progressions, but once again, we have to keep these expressions in mind because they will be used while solving the recurrence relations. We know an arithmetic progression where each term differs from the previous term by a constant difference. So if the Tn is the nth term of the series, A is the first term of the series, N is the number of terms, D is the common difference, then I can specify the nth term as A plus n minus 1 into D. The sum of the n terms are n upon 2, 2a plus n minus 1 D, or if L is the last term, then I can say Sn is equal to n by 2 A plus L. An example of arithmetic progression can be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is an arithmetic progression. Or 3, 5, 7, 9. This is an arithmetic progression. Geometric progressions, on the other hand, they are progressions where each term is a multiple of the previous term by some common ratio. Here, if R is the common ratio and A is the first term, then the nth term of a geometric progression is given by A R to the power n minus 1, and the sum of n terms is given by A multiplied by R to the power n minus 1 divided by R minus 1. Now these properties will be used while solving the recurrence relations. Right? So let's jump directly into. Now this is a recurrence relation. AK is equal to 2AK minus 1, and I have been given the initial condition A0 is equal to 1. Now I have to solve this recurrence relation. Now I have been given AK is equal to 2AK minus 1. Right? So I can specify it as 2 multiplied by 2AK minus 2. See, by the same logic, how can we define a k minus 1? A k minus 1 will be 2 into a k minus 1, that is 2 into a k minus 2. So this is a k minus 1 is equal to 2 a k minus 2. So if I substitute it over here, it becomes a k is equal to 2 multiplied by 2 a k minus 2. Again, it can be written as 2 multiplied by 2 multiplied by 2 a k minus 3, right? This could have been written as 2 square a k minus 2. I can write it as 2 to the power 3 a k minus 3, and so on. So finally, when I get to the say terms, as I go on solving a k minus 3, then a k minus 4, a k minus 5, and so on. So I can write it as 2 to the power k when I go up to k terms. When I solve up to k terms, so this becomes 2 to the power k a k minus k. Or what is a k minus k? It is a0. So that is 2 to the power k a0. So ak is equal to 2 to the power k a0, right? But still this expression is still using one of the previous terms, but this is where this initial value comes into picture. A0 has been given as 1, so this will be 2 to the power k into 1, so that is 2 to the power k. So I have ak is equal to 2 to the power k. Now this is an expression for the kth term of the series which is not using any previous term. So this is the solution for the recurrence relation. So 2 to the power k for all k greater than equal to 1. Let us go through the solution once again. AK, the recurrence relation has been given to us as AK is equal to 2AK minus 1, A0 is equal to 1. We'll go through this solution. First two solutions will go very slowly so that you get the hang of it. Right? Now, by the same logic, if I replace K by K minus 1, if I replace this K by K minus 1, so the expression becomes AK minus 1 is equal to 2A K minus 1 minus 1. 2A K minus 1 minus 1, or I can write it as 2A K minus 2. So if I write AK is equal to 2AK minus 1, now AK minus 1 I can substitute it as 2AK minus 2. So I get 2 into 2AK minus 2. So I can write it as 2 to the power 2 AK minus 2. Now by the same logic I can write AK minus 2 is equal to 2 AK minus 2 minus 1, that is 2 AK minus 3. So AK minus 2 is 2 into AK minus 3. So I get 2 into AK minus 3, 2 to the power 2 and 2 AK minus 3. So I get 2 to the power 3 AK minus 3. Then similarly I'll get AK is equal to 2 to the power 4 AK minus 4 is equal to 2 to the power 5 AK minus 5 and so on. When I cover k terms, I'll get to 2 to the power k A k minus k. See, 4, 4, 3, 3, 2, 2. So k and k. So I get 2 to the power k A k minus k. Now we know k minus k is 0. So I get AK is equal to 2 to the power k A0. Now A0 is our initial value which has been given as 1. So I substituted over here. So I get 2 to the power k into 1. So this gives me the solution to this recurrence relation. AK is equal to 2 to the power k for all k greater than equal to 1. Let's take another example. An is equal to Nan minus 1, A0 is equal to 5. If you remember, this was the example which we talked about earlier. Now, it has been given An is equal to Nan minus 1, right? By the same logic, if I say An minus 1 can be written as N minus 1, An minus 1 minus 1. So that is N minus 1, An minus 2. Similarly, An minus 2 can be written as N minus 2, An minus 3 and so on. Now, we'll substitute these values over here. An is equal to An minus 1 can be written as N minus 1 An minus 2 can be written as N minus 1 N minus 2 An minus 3 and so on. I can go up to An is equal to N minus 1 N minus 2 up to N minus k An minus k. Substituting k is equal to N minus 1. So I'll get An is equal to N minus 1 N minus 2 up to N minus 1 A n minus n minus 1. So this gives me n minus 1, n minus 2 up to 1 and a1. Remember what it is? This is the factorial. This is the expression for the factorial. So this I can write it as n factorial a1. So an is equal to n factorial a. Sorry, this will be a0, not a1. It will be a0. So n factorial a0. This is n minus 1. So this will be a0. Now a0 has been given to us as the initial value. Now I can write it as an is equal to n factorial into 5, or I can say as 5 into n factorial. So this is the solution for this recurrence relation. An is equal to 5 into n factorial. See, the solution for the recurrence relation does not use any of the previous terms. So let's take one more example. The recurrence relation has been given to us as an is equal to an minus 1 plus n, and the initial condition is given to us as a1 is equal to 4, right? So the recurrence relation is an is equal to an minus 1 plus n. Now say if I substitute, or if I replace n by n minus 1, so this becomes an minus 1 is equal to an minus 1 minus 1 plus n minus 1, which becomes an minus 2 plus n minus 1. Similarly, I can write it as an minus 2 as an minus 2 minus 1 plus n minus 2. So I can write it as n minus 3 plus, let's put it in brackets, n minus 2. So let's use the logic over here. So now it has been given to me as an is equal to an minus 1 plus n. Now I substitute the value of an minus 1 from this equation, from here. So I get an minus 2 plus n minus 1 plus n. Once again, I can substitute the value of an minus 2 from here. I can write it as an minus 3 plus n minus 2 plus n minus 1 plus n. Or I can also write it as, let's write it in a slightly different manner. I can write it as an minus 3 plus n plus n minus 1 plus n minus 2. I can go on doing this. So eventually I'll get n minus k plus n plus n minus 1 plus n minus 2, and so on. I'll go up to n minus k minus 1, right? When it was n minus 2, it was up to n minus 1. See, remember, it was n minus 2, so it was n minus 1. When it was n minus 3, it was n minus 2. So when I go up to n minus k, I'll go up to n minus k minus 1. So now this is the expression. An is equal to an minus k plus n minus 1 plus n minus 2, and so on, plus up to n minus k minus 1. Now let's substitute k by n minus 1. So I'll get ak is equal to n minus n minus 1 plus n minus 1 plus n minus 2, and so on, plus n minus n minus 1 minus 1. Solve it. You will get it as a1 plus n minus 1 plus n minus 2 plus 2. You'll get, solve this expression, you will get 2, right? Now I have this expression. Now let's do one thing. Let's add and subtract 1 from the expression. What I'll do is I'll add 1 to this expression, and I'll let's do one thing. Let's write it in the next step. Let's write it like a1 plus n minus 1 plus n minus 2 plus 2 plus 1 minus 1. Now see this expression, see this series from here to here, see this series. This is the sum of n numbers, so can be written as a1 plus n into n minus 1 divided by 2. Remember, the sum of the n terms is n into n minus 1 divided by 2 minus 1. So ak is equal to a1 plus n into n minus 1 divided by 2. But a1 has been given to us in the form of initial condition as 4. So I can write it as ak is equal to 3 plus n into n minus 1 divided by 2. Sorry, not 3, 4. It has been given as 4 minus 1. So this can be written as 4 minus 1 is 3. 3 plus n minus 1 divided by 2. This is the required solution. So the solution for the recurrence relation ak is equal to 3 plus n into n minus 1 divided by 2. This is the solution of the recurrence relation. Let's take another example. Now this example is different from the previous ones, as here what I'm doing is I'm having the expression, the general expression, and I'll try to find the recurrence relation for this. The expression that has been given to me is ck is equal to 2k square plus 1. Let's call it equation number 1. If I substitute k by k minus 1 over here, I get ck minus 1 is equal to 2k minus 1 whole square plus 1. Let's solve it. You get 2k square plus 1 minus 2k plus 1. Still solve it further. You get 2k square minus 4k plus 3. By the same logic, ck minus 2 becomes 2k minus 2 whole square plus 1, that is 2k square plus 4 minus 4k plus 1. Solve it. You get 2k square minus 8k plus 9. Let's call it equation number 2. And let's now do one thing. Let's multiply this ck minus 1 by 2. So 2 of ck minus 1 now becomes 4k square minus 8k plus 6. See, what I'm doing is I'm multiplying this equation by 2. So this now becomes my equation number 3. Now I'm ready to go and look for my recurrence relation. Now add equation number 1 and 2 and subtract 3. We get one is ck plus ck minus 2 minus 2ck minus 1. This is the left hand side. On the right hand side I get ck. The equation number 1 was 2k square plus 1. Equation number 2 was 2k square minus 8k plus 9 minus equation number 3 is 4k square minus 8k plus 6. Let's solve the right hand side. I get 2k square plus 1 plus 2k square minus 8k plus 9 minus 4k square plus 8k minus 6. Now 2k square plus 2k square, 4k square minus 4k square is 0. So k square terms becomes 0. Similarly, 1, let's take the k terms, minus 8k and plus 8k. So k terms also cancel out. So I don't have any term with k square. I don't have any term with k. Now let's see the constant terms. 1 plus 9, 10 minus 6, 4. So I get 4 over here. So now I'm left with the expression ck plus c k minus 2 minus 2 c k minus 1 is equal to 4. So this is the required recurrence relation for this expression. You can check it the other way around also. If you have been given this recurrence relation, you can identify that this particular recurrence relation will have this solution. This will be the solution for the recurrence relation. So that's all about the iterative method of solving the recurrence relations. In the next session, we are going to talk about the other method. Right? Till then, thank you.